All right, if not, then we will dive into content from this week. So I sent out a handout on Piazza, so you all can go and refer to these notes afterwards. And then I'll have the same format where we go through some of the questions together, and I'll also send out those notes afterwards. So one thing we, is the screen share working for you all? I don't know why it's not working for me. Do you all see the notes? Or do you see a blank thing?
Please. There's a PDF icon on the screen.
Okay, let me see what's going on. That's really weird. All right, I think that's working now. Cool. So last week we covered a lot of sort of counting techniques for counting permutations. For example, we'll do a really quick review, but this week we're going to talk about slightly more complicated techniques. So how do we correct for overcounting when there's more restrictions in what we're trying to count? And we'll learn about symmetry as well. And then we'll also talk about combinations, which are sort of, and how they're different from permutations, but they're a different way of counting in other types of problems where you're picking things in a different way, maybe when order doesn't matter. So we'll go into that a little bit later in this lecture as well. So it seems like whenever I switch tabs, this breaks. Cool. So this was the handout. And basically, let's take a look at an example to think about like how we might overcount with some cases. And then we'll kind of generalize from the example to figure out how we would take care of this in the general case. So basically in some problems, we have to understand when we might run into issues if we only rely on multiplication to count. And so let's look at a very simple example. And here, I actually think I will have more space if I go to the other one. So sorry about this. Cool. So here's a pretty simple example, and let's do 1A together. So this should be review from last week, and it's just find the number of distinct arrangements of the letters in the word tin, so just T-I-N. Can anyone tell me how to do that?
It would basically be 3 factorial ways to arrange distinct arrangements. So 6 distinct arrangements because of the fact we have 3 options, and each time we use one, the amount of options left decreases.
Yep, that's right. So we could think about it as there's 3 letters. For the first letter, there's 3 choices. For the second letter, there's 2 choices, or for the first letter, there's 1 choice. Or if we remember the idea of permutations, this is a way of permuting 3 things from 3 things. So that was 3 factorial, which is 6. This is the same. So then let's talk about case B. So it says find the number of distinct arrangements of the letters in the word T-I-N-T. So in this case, it's a little bit different because there's 2 T's. And so we might be tempted to think, okay, the answer is 4 factorial. But that would actually be overcounting. Does anyone see why?
There's 2 T's instead of 1. So sometimes you might forget that there's another T there and you would count it as 1.
Yeah, so you could actually count the T's. So we could do an exercise together just to see. So here we have the letters T-I-N-T. And just to be clear, I'll label one of them like T1 and T2. And so if we were to permute these, we could start listing out all the different possibilities. I won't list all of them, but we could have T1, I, and T2, T1, I, T2, N, T1, N, I, T2, etc. And then later on, we might also have the permutation T2, I, and T1, T2, I, T1, and T2, and I, T1, etc. So when we label the T's 1 and 2, we can see that these are different permutations, but the problem doesn't have different T's, it has the same T. So if we count using 4 factorial, we're going to count these words twice, because here we're counting T-I-N-T, and then here we're counting T-I-N-T again. And we count T-I-T-N twice, we count T-N-I-T twice, etc. So for each distinct arrangement of T-I-N-T, we're actually counting it 2 times. Does anyone see why that's the case?
Yes, because of the fact that T-I-N-T, no matter which T that's starting or ending, it's still the same word in the same arrangement.
Right, yeah. So basically for every arrangement, we can either have T1 something and then T2, or we can have T2 first and then T1. So when we actually want to count how many total arrangements there are, one exercise you all can do is list out all the arrangements and check. But here we can do 4 factorial to take into account all of these. But then we have to divide by 2, because we know that for everything we're counting, there's 2 for each. So here we want to divide by 2, and then we get 12. And so another way to think about 2 here is, like in this case, there's 2 we see because there's T1 and T2 and T2 and T1. But let's actually go through another example where there's 3 and see how this generalizes. But one sort of thing I'll note here is when there's 2 T's, the reason it's 2 is because there's 2 ways to arrange the 2 T's. And so if we were to generalize this, let's say there's 3 T's or 4 T's. If there's 3 T's, there's actually going to be 3 factorial ways to arrange the T's. Or if there's 4 T's, there's going to be 4 factorial ways to arrange the T's. So to be a little bit more precise, I might write this is actually over 2 factorial, which is the same as 2. Any questions? If not, I'll move on to another example just to make sure we all get this concept.
Yeah, I kind of have a question about B.
Okay, yeah, what's up?
Okay, so for example, just if it was T-I-N-E, the answer would be 4 factorial, right? Okay,
Yes.
so what I'm confused about is basically, since now every word we can form with TINT, it has 2 options, I guess. So I'm confused as to why it's divided by 2 factorial and not multiplied by 2 factorial.
Yeah, it's a good question. Let's try working this one out. Kind of need more room. I'm going to use this space down here. So let me actually write down all the combinations. So we have T, I, and T. And I'm going to label the T's T1 and T2, but there's not really a difference between the T's when we want to count the final answer. And so I started listing them out above, but let me actually write them out. So T, I, N, T, T, I, T2, and let me know if I'm missing one, but I'm going to try to be pretty systematic about this. So here I'm going to start everything that begins with T1. I'm going to list it all out. And then next I'm going to list out everything that begins with I. Oops. Just trying to keep this in order. And then we'll list everything that starts with N. And then finally, I'll list everything that begins with T2. Okay, so if we have 4 different letters in this case, then we talked about how we have 4 factorial different arrangements, and 4 factorial is 24. So here we can verify there's actually 24. There's 4 columns, and then there's 6 combinations in each one. So does everyone see these are the 24 arrangements?
Yeah.
Is there any that I'm missing? Okay. So now we can take a look at what we're overcounting here. For example, I'm gonna circle a couple that are the same. I wish I could have different colors here. Maybe yellow. So for example, TINT is being counted twice, here and here. Another example is TITN is being counted twice here. TNIT is being counted twice here. TNTI is being counted twice. TTIN is counted twice. And TTNI is counted twice. And the reason it's counted twice is for every combination, we actually have, or for every permutation, I should say, we actually have T1 and T2, and we can always flip where T1 is and T2 is. So that gives us 2. And then we can also see for the ones that begin with I and N that there's everything's counted twice as well. I put it in a kind of a different order, but if we look at I, T, N, T, we have it here twice. If we look at I, T, T, N, we also have it twice. And then if we look at I, N, T, T, here we have it twice. And then lastly, for N, T, I, T, we have it here and here. N, T, T, I, we have it here and here. And N, I, T, T, we have it here and here. So if we list out everything, we actually see there's actually only 12 distinct arrangements. So I underlined a bunch of, all of them at this point, but we can see that these are all distinct. And then these are distinct. And then these next four are copies of the previous three. Sorry, those three are copies of the previous three. These three are distinct. These three are copies of those previous three. And then these six are copies of the six that I starred on the left. So if we count how many I starred, there's actually only 12. So that's how we would get 12 if we were to list everything out. If we didn't want to list everything out and kind of wanted to figure out how to generalize this, we would take 4 factorial and divide that by the number of permutations that we could permute the two t's. In this case, that's 2 factorial. So we would take 24 factorial and divide, 24, which is 4 factorial, and divide that by 2 factorial, which is 2. To give us 12. And this is the number of ways to arrange T1, I, and T2. And this is the number of ways to arrange T1, T2.
Yeah, okay, so basically I just understood that we're supposed to treat the T as like the same alphabet, not as T1, T2. That's where I got confused.
Yes.
Thank you.
All right, so let's take a stab at this question, which I wrote under here, but find the number of distinct arrangements of the letters in the word feeder. So that's F-E-E-D-E-R. So can anyone take a stab at this one? We'll do it together.
Could I try?
Yeah.
So feeder has 6 letters. So but 3 are repeated.
Mm-hmm.
So that'll be 6 factorial divided by 3 factorial. And then the 3 factorial cancels out when you expand.
Mm-hmm.
So it'll be 6 times 5 times 4. And that's 120.
Yep, that's right. So this is the same idea. Basically, there's 6 factorial ways to arrange feeder if the 3 E's are different E's, but in fact, they're the same letter. So to correct for the overcounting, we look at how many ways are there to arrange, say, E1, E2, E3. And there's 3 factorial ways, which is 6 ways to arrange that. And then we look at how many ways are there to arrange F, E1, E2, D, E3, R. There's 6 factorial ways to arrange that. So when we divide, we get 120. Any other questions on this? All right, so I have one more question that's a little bit trickier. So this one says, how many distinguishable arrangements of the letters in contest have both the vowels first? So here's an example. For example, O, E, T, C, and S, T is one such arrangement because we have O and E as the beginning. And then O, T, E, T, S, and C is not because both the first 2 letters are not vowels.
Could I try?
Yeah.
So you could permute the first O and E, which would be 2 factorial. Then you permute the others, which is 5 factorial.
Okay. So the other letters are C, N, T, S, T. And so here we see there's 2 T's. So how many ways are there to permute the others? You have the right high-level idea, but we actually have to correct for overcounting in the others.
Then we also divide by
You could,
Yeah, you could divide the whole equation by 2 factorial since there are 2 T's.
Right, yeah. So we divide this by 2 factorial. So here, just as, was it David that said that? Explained,
Yes.
there's 2 factorial ways to permute the O and the E. And that's OE and EO. And then there's this many ways to permute C, N, T, S, T. So this gives us 5 factorial, which is 120. Awesome. All right, so we talked about overcounting in this case, in these examples, when there's sort of multiple things. And this is how you correct for overcounting when we're permuting things and there's like multiples of the same thing that we're permuting. Now we'll look at a different way of overcounting, which is basically if 2 or more arrangements are the same because of some type of symmetry, then we may also have to correct for overcounting. And so let's look at an example of what kind of symmetry is possible. So here's an example question. So it says, how many distinct ways can 6 people sit around a circular table? And then in this case, we want to count 2 arrangements to be distinct. If some person has a different neighbor to their right or to the left in one arrangement than the other. So I'll just walk through this example. If we look at so if you remember the question of like, oh, how many ways are there to arrange 6 people in a row? It's kind of the same as like permuting 6 things. So we might say, okay, there's 6 factorial ways to do that. And that's like if I started labeling or listing out stuff in order, like 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 6, 5, 1, 2, 3, 5, 4, 6, etc. But now we have it actually, instead of sitting in a row, we have it sitting around a circular table. So I'm just going to draw our little circle. And so let's say we take a permutation 1, 2, 3, 4, 5, 6, and that means we're going to seat the people like 1, 2, 3, 4, 5, 6. Then later on, when we have the permutation 2, 3, 4, 5, 6, 1, and we seat those people, we might seat them 2, 3, 4, 5, 6, 1. So in these 2 cases, people are actually at different seats, but according to the definition of the problem, this is actually the same arrangement. And the reason for that is we defined it as distinct if some person has a different neighbor to the right or to the left. And in this case, everyone has the same neighbor. Like 1 is sitting on their left has person 2, on their right has person 6. For number 2, their left is person 3, their right has person 1, etc. So basically, you get the second one just by rotating the first one. And so we can see in this case, we're actually overcounting. Can anyone name another permutation that would overcount the same arrangement? So,
4, 5, 6.
Yeah, so 4, 5, 6, 1, 2, 3. Yeah. So that would also give us 4, 5, 6, 1, 2, 3, and that's the same arrangement as well. And then in fact, we actually have 6 different ones. So here we have 3, 4, 5, 6, 1, 2 would give us the same one, 5, 6, 1, 2, 3, 4 would give us the same one, and 6, 5, 1, 2, 3, sorry, 6, 1, 2, 3, 4, 5. So here, 3, 4, 5, 6, 1, 2, 5, 6, 1, 2, 3, 4, and 6, 1, 2, 3, 4, 5. So does everyone see why these 6 arrangements are actually all the same?
Yeah.
Cool. So in this case, we see if we just said 6 factorial, then we're overcounting because every arrangement, it could actually be counted 6 times because of rotational symmetry. So in order to get the right answer here, we actually want to divide by 6 because there's 6 ways that we could sort of rotate the seats. So we take one order and we can kind of rotate it such that each person sits in the seat with the same order, the same sort of arrangement. So to get the final answer here, we actually want to divide 6 factorial by 6 to account for this rotational symmetry. And this would give us, let me write down here, 6 factorial over 6 equals 5 factorial, which is 120. And I had a note here, but basically because the arrangements in this problem can be rotated to produce identical arrangements, we call this type of symmetry rotational symmetry. So it's just a term you might see. Any questions? Let's do another question together that's similar, but also a little different. It's a little trickier. So this one says, in how many ways can 5 distinguishable beads, so distinguishable means you can tell the difference. Maybe we can say they're like 5 different colors. How many ways can they be placed on a leather bracelet? And then we decide that they're indistinguishable if I can take the bracelet and wear it with the beads in the same order. So does anyone have any ideas on how to do this one?
I guess it will be 5 factorial divided by 5.
5 factorial divided by 5. Why is that?
Well, because 5 distinguishable beads, so that's basically 5 factorial. And then divided by 5 because it's said in the same order. So like the previous example, how we change the order of the beads. Like it's the same placement, just that they're, how do I explain it?
Rotated or?
Yeah, they're just rotated.
Yeah, so that's right. That takes into account rotation, but let me just show one more thing that happens in this case that doesn't happen in the previous case. So let's look at the arrangement 1, 2, 3, 4, 5. And say these are, we'll just number the beads. Then let's look at the arrangement 1, 2, 3, 4, 5. So in this case, we would count these as distinct ways that the beads are on the leather bracelet because they're in a different order left to right. And also in the previous case when we're like counting people sitting at the table, this is also different. But one thing that's kind of different about a bracelet that's kind of a tricky part of this question is for bracelet, you can actually flip it inside and outside. So I can take a bracelet in some order and then turn it over. And so if I turn it over, that flips what is on the left and what's on the right. So if I,
Yeah, so you just like can wear your watch upside down.
yeah. So you can wear it the other way around. So if I take this bracelet, 1, 2, 3, 4, 5 on the left here, these are the beads, and I flip it the other way, then I'm going to get this. And so now we need to correct for this other kind of overcounting, which we can call flip symmetry, because we flip the bracelet.
Then can we divide it by 2? After dividing it by 5.
Yeah, that's right. So we want to also divide this by 2. So this gives us 4 factorial divided by 2, which gives us 24 divided by 2, which gives us 12. Any questions on this? All right, let's do one more kind of symmetry one, and then we'll move on to a different concept. So this one says each face of a regular tetrahedron, which is a triangular pyramid, is painted a different color. We'll say like red, white, blue, and orange. So how many distinct arrangements of colorings are possible? So I don't know if everyone knows what a tetrahedron is. I'll do my best to draw one out here. But basically, a regular tetrahedron means, and you might see this in geometry as well, but I'll give a quick intro. A regular tetrahedron is a 3D object, and each face is a regular triangle. So basically, an equilateral triangle. And then basically, you have a base here. That's a regular triangle, and then you have 3, sorry, that's a bad line. You have 3 faces that are all triangles. So does everyone see that shape? So we have 4 faces, and then 3 plus a base, and all of the bases, or all of the faces are the same because they're all equilateral triangles. So now we want to see how many ways can we paint this tetrahedron 4 different colors, 1 per face. Anyone have any questions about what a tetrahedron is? All right. So any ideas on how we could do this one? There's some rotational symmetry we have to account for here.
Well, first off, there are 4 different colors. So first we'd start with 4 factorial. And then because of the fact that the tetrahedron can stand on its 4 different side faces, then we'd have to also account for the fact that it stands on its 4 different faces and divide by 4, I think, so that we can get the accurate number of distinct arrangements.
Yeah. So we can see there's 4 factorial ways to just pick 4 colors in some order. And then you're right, we have basically, let's look at this bottom face, which is this one. For each sort of tetrahedron, we could have put it so that the bottom is that color. So we need to divide by 4 to account for overcounting there. But then one more thing we're overcounting is, say we picked a color for the base, and any of the 4 faces could have started in the down position. We can also rotate it along this axis, because we could take each one and kind of turn it. And so there's actually 3 ways to do that, even with some fixed color in the base position. So what that means is we actually have to also account for that by dividing by 3, because there's 3 ways that you could rotate it. Does everyone see why that's the case?
Yeah.
So in this case, this actually gives us, there's only 2 distinct ways.
I'm sorry, but I'm not sure I quite understand this one.
Yeah, so there's 4 colors here, red, white, blue, and orange. And so if we wanted to just, let's say we want to number the faces, 1, 2, 3, and 4. Sorry, it's hard to tell what I'm numbering. Let's number the bottom face 1, this front face 2, the side face 3, this back face 4. So if we wanted to just color each one based on the number, then we would get 4 factorial. But since we can rotate a tetrahedron around and kind of put it wherever, for some color, let's say like orange, we can always place the orange face down regardless of where we started. And so we're counting that 4 different times, because if we color, let's say we color face 3 orange, we can always rotate it so that face 1 is orange. So in that case, we're overcounting by 4, a factor of 4. So we want to divide by 4. At the same time, whenever we have the orange face down, we could still rotate so that, say, the red face points any face we choose. So let's say we colored this one orange and this one red. That's the same as if we, let's label all of them. Let's say this is white, this is blue. That's the same as if we colored this one orange, this one red, this one white, and this one blue. It's just that we rotated it. And so in that case, there's actually 3 rotations that we haven't accounted for. So we need to also account for that.
Yeah, that makes sense. Thank you.
Yeah, it's a little bit hard to visualize, but you can also, if you have some sort of physical object, maybe you can like try labeling them and see that you can turn it around. Awesome. So now let's move on to a different type of counting. And I'm gonna try, cool. I got this switching thing to work. So this is going back to the lecture notes. And I want to talk about a different technique to solve counting problems that we call complementary counting. And one way to think about this is, let's use a practice problem here. A large cube is painted green and then chopped into 64 smaller congruent cubes. How many of the smaller cubes have at least one face painted green? And so one way we could do this is using a, sorry?
I can't see the screen.
Oh man, still not
Yeah,
working.
me either.
All right, sorry about
Me
this.
neither.
How about now?
Nope.
No, it still hasn't changed.
Yeah, now I can see it.
All right. Cool. So yeah, the term I was talking about was complementary counting, spelled like this. And in order to explain this concept of complementary counting, let's consider an example problem. So here there's a problem. It's from a test in Alabama, which is one of the math contests here in the US. A large cube is painted green and then chopped up into 64 smaller congruent cubes. How many of the smaller cubes have at least one face painted green? And so let me just draw this out. So we all know what we're talking about. So we have this cube. We paint it green and then we cut it into 64 cubes. So that means there's actually a 4 by 4 by 4 cube here. So it's kind of like this, that we chopped it up. And so one way we could count this is using a technique that we learned last week called Casework. We could count the number of smaller cubes with 1, 2, and 3 painted faces. But that's actually a lot of cases. Maybe there's some chances that we make an error when we're counting. And instead here, we might realize that it's actually easier to count the number of smaller cubes that have no painted faces, and then subtract that from the total number of smaller cubes. So this method basically is like counting what we don't want instead of counting what we do want. Here, we call this complementary counting because we're counting the complement. So in this case, we might look at, okay, how many cubes have no painted faces? And the only cubes that have no painted faces are sort of the inner cube within the 2 by 2 by 2 cube that doesn't have any faces touching the outside. And so here, since it's a 2 by 2 by 2 cube, the total number of cubes that don't have any paints is 2 cubed, which is 8. And then the total number of cubes that we have overall is 4 cubed. So to get the final answer, we can subtract 2 cubed from 4 cubed to get 56. Does anyone have any questions about this example? And we can see this is actually a lot easier than if I said, okay, let's do the casework of 1, 2, and 3 painted cubes, right? Because if we want to do that, we're sort of solving 3 problems and then adding them together, and we have to make sure that we're counting each one correctly.
Miss Wendy, can we also just, based on the fact that there's 16 cubes on each face, and each of the cubes on the outside of the center or of each face will have more than one green face. So could we say that the 2 by 2 square formed in the center holds all the examples that would have would have one green face because of that?
Yeah, so basically you're saying if we count directly, then we have to count the different cases, right? So you said there's 4 on each face that have 1 painted side. And so if we did it that way, we'd say, okay, for how many have exactly 1 painted face? Let's write it up here. 1 painted face. You'd have to say, okay, there's 4 per side, and there's 6 sides, so that's 4 times 6. And then you'd also have to count, since it says at least 1 face painted green, you'd have to also look at how many have 2 painted faces. And then that is on every edge, there's 2. And there's, I think there's 12 edges, right? So that's 2 times 12, which is 24. And then for 3 painted faces, that's every corner has 3 painted faces. So that's 3.
Don't we overcount the edges that way because of the fact of the corner? Because if we look at the edges and we look at the 2 faces, aren't we also adding the fact that the corner is also on the edge in a way? So wouldn't we overcount the corner piece in the edges case?
Yeah, so that's why counting in this case, we want to use complementary counting, because you have to be very careful not to overcount. So if I were to do this without complementary counting, I had to be very careful for 1 painted face that I'm only counting the 4 in the center, and then I'm not counting also these faces. So that's 4 times 6. And then when I'm counting the edges, then I'm only counting the edges. So I'm counting only 2 instead of counting 4. And then when I'm counting 3, I'm counting just the corners, and there's 8. So if I sum 24 plus 24 plus 8, that would give me 56. But in this case, if we use complementary counting, all we have to do is subtract out the sort of inner 2 by 2 by 2 cube from the bigger 4 by 4 by 4 cube. And so if I subtract that out, I have to consider fewer cases. And so it's just an easier way. It's not that you can't get the right answer using the other one, but the other one just might take longer time, and you have to be much more careful about things like what you said, like making sure we're not counting the edge and the
Miss
corner.
Wendy,
Yes.
but the question says how many of the smaller cubes have at least one integrity, not how many faces. So shouldn't the ones in the middle be 4 cubes? Instead, then we subtract from 6, given 60.
Are you talking about the complementary counting approach, or the approach where we count all of them directly?
The complementary counting approach, because the question is looking for how many cubes and not how many faces.
Right, right. Yeah, so the reason we subtracted 8 is because the part that has no painted cubes is this like 2 by 2 by 2 cube that's in the middle of the 4 by 4 by 4 cube, if you can visualize that. Because we've painted all the outside. And so any of the outside cubes will have at least one face painted. And so the only cubes that don't have any faces painted are the cubes in the very center of your larger cube. And so that is a 2 by 2 by 2 cube.
Okay, thank you.
Yeah. So in this case, like this is just one technique that I want to add to your toolkit. Like not every problem can be solved with complementary counting, but now that you know what complementary counting is, when you see some question, especially when there's a lot of tough casework, sometimes the easier way is to count the complement. And so we can do a couple more examples just to get a hang of which types of counting problems will be easier to do via complementary counting. And so these notes, you can refer back to them. They're in the PDF that I shared on Piazza. But here, let's do a couple other questions. So here's a different counting problem. It says Russell goes on vacation and takes 5 shirts, 5 pairs of pants, and 5 hats. Each item is one of the same 5 colors, so that Russell has one of each item of clothing in each color. So in how many ways can Russell choose an outfit? Sorry?
I can't see the question.
You can't see the question? Can anyone, can other people see the question? It appears to work for me right
Yes,
now.
please.
I can see the question.
It's loaded in. Sorry, it's just my internet, so it's loaded.
Oh, no worries. Okay. Yeah, so basically Russell has 5 shirts, 5 pairs of pants, 5 hats. Each one, he has it in 5 colors, in the same 5 colors. And then it says, how many ways can Russell choose an outfit of 1 shirt, 1 pair of pants, and 1 hat for his first day of vacation if he doesn't want all 3 items to be the same color? So anyone have any ideas on how we can do this one?
Well, you could say that in total, we could multiply we could say 5 cubed, the different arrangements Russell can have for his clothing. So there are 125 ways in which he can combine his hats, his shirts, and pairs of pants. And then if we look at the items that will be the same color, it will most likely be, you can only match one color with another color and another color. So we would say that there are 5 different ways he can pair them so that each of them are matching the same color, and subtract it from our total 125 to get 120 ways you can make an outfit without the same color.
Yeah, awesome. So just to summarize, what is it? Solorm, is that your name? What he said, there's 125 total outfits, 5 outfits of these total outfits that have the same color because there's only 5 colors. And then to get the total number of outfits that don't have all 3 items to be of the same color, we can just subtract out 5 to get 120. Awesome. And here we could see if we didn't use complementary counting, what we'd have to do is kind of this casework again. We'd have to figure out, okay, how many ways are there for Russell to choose an outfit that has like all of them different colors? And then what if they were like 2 that were the same color? And then we'd have to sum those up, which in this case, it's doable, but it's much more straightforward to think about it this way. Let's do another question. How many 4-digit positive integers include at least 1 3 as a digit? So any ideas from people on this one?
Well, we can't count all the 4-digit positive integers. We can know that they range from all the way from 1,000 to 9,999. Those are all the 4-digit positive integers. And then we know that in every 10 of those integers, there will be 1 of them that contains a 3. And so there are 10. If we separate 10 between 100, 1,000 and 1,100, 10, and then we know we're doing up to 999. So we do 10 times 8 so that we find out that from 1,000 to 8,000, there are 80 different ways of us doing it. And then we just count the ones between 8,000 and then 9,900, add them together and subtract from the total amount of integers.
Sorry, how are you counting the ones? Okay, so let's break this down into a couple parts. So the first part of what you said is how many total 4-digit positive integers are there? And here we noted the range is from 1,000 to 9,999. So how many total is that?
That's 9,000 in total.
Right, so this is 9,000. There are a couple ways you could count this, just to summarize. You could count it like the way that we learned last time, which is you take the top one, subtract the bottom one, because it's a sort of simple list here, and then add 1, you'll get 9,000. Another way that you could count this is you could think about there's actually 4 digits, 4 digits, and there's 9 possible choices for the first digit, because it could be 1 through 9, and then you have 10 choices for any subsequent digit, because it could be 0 through 9. And so either way, this gives you 9,000 total 4-digit positive integers. And then in this case, what's the complement that we're counting?
We're looking for all the ones that don't have 3.
Right, so we want to look at how many numbers 4-digit numbers have no 3. So how can we count this one?
Well, we could.
Oh, go ahead.
We could track and put like we do to find the total 4-digit positive integers. We would just pick a random position. We would look at the positions and then we realize that there are 10 possible numbers that can go there, but we can't exactly use 3. So it becomes 9 to the power 4. So we just do 9 times 9 times 9, and that would give us the total amount of 4-digit positive integers that don't have 3. And then we subtract that from the 9,000.
No, I don't think that's true because the first number doesn't have 0 and 3, so it will be 8.
If someone's talking, could you talk a little bit louder? I can't really hear, but I can hear that you're trying to say something.
The first number will only have 8 integers because you can't add 0 and 3. And the
Right.
rest of
Yeah.
the numbers will have 9 because you can't add 3. So it will be 8 times 9 times 9 times 9, which will give you 5,832.
Yeah, awesome. So you guys both have the right idea, and that's right. So if we look at how many 4-digit numbers have no 3, we can take the same approach as we did up here and look at how many possibilities we have for each digit. For the first number, we have to make sure that it can't be 0 as well. So if we look at how many possibilities there are, it's just 1, 2, and then 4, 5, 6, 7, 8, 9. So there's only 8 possibilities. And then for the rest, there's 9 possibilities because it can also be 0. And then I think Na had said that it was 5. This is 5,832. So to get the total answer here, we can take 9,000 and subtract 5,832. And this gives us 3,168. Cool. Any questions? If not, we'll just do one more on complementary counting. All right, let's do this one. So this is another one where people are sitting in a row. How many ways can these 6 people, Allison, Jennifer, Tony, Wesley, Anshu, Xinke, sit in a row of 6 seats if Tony and Wesley refuse to sit next to each other due to their bitter disagreement over whether chocolate ice cream tastes better than vanilla ice cream? So basically we have 6 people sitting in a row, and then 2 people don't want to sit next to each other. Any ideas on how we could do this?
Well, we can look at the different positions in which they could say, if we were to just draw out the 6 seats, and then we know we can have, and we look at how we can separate Tony and Wesley. So Wesley can be in the first, and Tony can be in the third, or Tony can be in the first, Wesley can be in the third. Tony can be in the third, and Wesley can be in the fifth, and so on and so forth. And then we try, and we know that the total, and then we know the total, we try and find the amount of people left and then multiply. And after doing that, we get the total number of arrangements.
Okay, so yeah, in this case, we want to do 2 different cases again. So we see the total number of arrangements is just 6 factorial because there's 6 people. And then here, what's the complement that we might want to be counting?
How they can all sit, how Wesley and Tony can sit together in every different way.
Cool. So we want to count the number of arrangements where Tony and Wesley sit together. And how do we count that?
Well, we could try and draw out the seats, and then based on how the seats are done, it could be Tony and Wesley are sitting together, or Tony being in seat 1, Wesley being in seat 2, or Wesley being in seat 1, being seat 2, And then we just go on and on until we've mapped out the different ways in which they can sit together and subtract that from the total in which they can't sit together.
Yeah, so let's see how to count this one. So in this case, since we want Tony and Wesley to sit together, we're really only permuting 5 things. We're permuting basically Allison, Jenny, the combination of Tony and Wesley, Anshu, and Sinke. And so we can arrange these 5 things in 5 factorial ways. And then, as was mentioned, for Tony and Wesley, we can arrange them as Tony and Wesley or Wesley and Tony. So we want to times 2 for that. So this gives us 240. This gives us, whatever this is, 720. So then if we subtract out the complement, then we'll get the number of ways in which they can sit together when Tony and Wesley don't sit next to one another. So this gives us 720 minus 240, which is 480. Any questions on that one? So I just want to conclude this section by saying, again, like, this is often a good technique if you read a question and you say, okay, looks like I have to do a lot of casework. Before you dive into the casework, it's a good chance to take a look at, like, well, is it easier to count the complement? Sometimes you do have to do the casework, but sometimes this can save you a lot of time.
Miss Wendy, could you please repeat that? I think I had a little network problem.
Oh, no problem. I just want to say, sort of in conclusion of this section, that this is one really useful technique that you all can use when you see counting problems. And oftentimes, if you see a counting problem where it doesn't look very straightforward to directly count what you're looking to count,
Miss Wendy,
and you end
I
up...
can't hear you if you're saying anything, but I can't hear you.
Can anyone else hear me?
Yeah, I can hear
I
you.
can.
Okay, let me
hear,
repeat. Oh, go ahead.
if you can't hear anyone, then you should probably just leave and come back.
Or maybe you can try increasing your volume.
Yeah.
Sometimes it happens.
If you're going to tell them what to do, I think you say it in the chat, because since they can't hear you, they wouldn't hear
Yeah, I realized.
Yes. All right, I'll just repeat what I said, and then if people have questions afterwards, we can talk on Piazza too. But basically, this is a good technique for you all to just kind of have in your toolbox. Basically, whenever you see a counting problem, if it doesn't look super easy to count directly, you can think about whether casework would be a good option, or potentially counting the complement. Sometimes you may still have to do casework. You can't avoid all casework, but just keep an eye out for when it might be easier to count the complement. So I want to cover another topic, and so I want to switch to here and scroll through these notes to this. It's a little bit different, but it's also a very, very useful concept in counting. And so it's called the principle of inclusion-exclusion. It's commonly abbreviated
I still
as...
can't hear you.
Can someone message him in chat and maybe tell him to try rejoining? Thank you. Or check that they're not on mute, or check that their volume is up. So this principle of inclusion-exclusion is often abbreviated as PIE for short. So if you ever see that, but it's a very, very useful principle. And so we can again use an example to learn about this. So let's consider this pretty common counting exercise, which is, say, we have a bunch of residents of a small town, we'll call them Mathville. 45 of them love popcorn, 57 of them love chocolate, and 23 of them love both popcorn and chocolate. So how many of them love popcorn or chocolate? And so when we say or, that means we need to include people who love just popcorn, we need to include people who love just chocolate, and we need to include people who love both popcorn and chocolate. And we have to make sure not to overcount. And so I don't know if you all have seen what we call a Venn diagram before.
We've learned it.
Basically, okay, awesome. So basically you can use Venn diagrams to see and count the overlaps. So here on the left, we have how many people like popcorn, how many people love chocolate, and then to fill in each part, we take the total number of people who love popcorn, which is 45, subtract out how many love both, and that gives us how many people love just popcorn over here in this section. And then we have how many people love just chocolate in this section. So it's 57 minus 23. And then for the last section in the middle, we have the people who love both. So in order to count it without overcounting, we can just take the left side, which is 45 minus 23, plus the right side, which is 57 minus 23, plus the middle, which is 23. And this gives us 79 people who like popcorn, chocolate, or both. So here we see the numbers actually reflect, basically we're summing up just popcorn, just chocolate, and both. But if we basically like save this computation to the end, we see another way to write this is how many people love chocolate, or sorry, how many people love popcorn, how many people love chocolate, and then we subtract out how many people love both. So that's reflected here. We can look at it by saying we're actually summing, it's equivalent to summing all the popcorn lovers plus all the chocolate lovers minus people who love both. And that gives us the total of popcorn or chocolate lovers. Another way to look at this is we can go about the counting process in just like counting as simply as possible. So let's first count how many people love popcorn, then count how many people love chocolate. So that's like this number of popcorn lovers here, number of chocolate lovers here. And so if we are adding the sizes of these two sets, if we look at the Venn diagram, what happens is we actually count the center part 2 times, because we count it once when we count this circle, and then we count it again when we count this circle. And then this leads to us actually overcounting. So we actually count this intersection twice, and we can use set notation to more formally say this. But in order to find what we call the union of the two sets, which is in this case popcorn or chocolate lovers, we actually need to subtract out the overcounting part, which is the intersection. And so here's another way of writing it over here. So this U symbol means union. And that just means if I take set A and set B and only count everything in there once, and these bars, this is referring to the size of the set. So basically the union of A and B, the size of that is equal to the size of set A, in this case, the size of the people who like popcorn, plus the size of set B, so this is the number of people who like chocolate, and then I have to subtract out, this notation means intersection. So this is how many elements are in both A and B, so I have to subtract out the center part to get the size of the union. So if we use this to the problem above with the popcorn and the chocolate, we see that there's 45 people who love popcorn, 57 people who love chocolate, and 23 who love both. So we can subtract that out and get 79 again, which is the same answer that we got here. And so this method is generally known as the principle of inclusion and exclusion because we're counting how many people inside and outside to get the union. Does anyone have any questions on this question or kind of the general notation here? All right. So you guys might be wondering, like, okay, that's kind of the same, like it's only maybe slightly faster, if at all, when I have two sets. So let's look at how this could be faster when we have maybe more sets. And so basically the advantage of using this principle is just like, it'll help you a lot more when we're looking at, say, like sets, 3 different sets or more, because you actually end up with a lot more cases in that case. So here, let's look at an example for 3 sets and how the principle of inclusion and exclusion generalizes. So let's say we have this school. Many people take some AP or advanced placement math and science exams every year. And we'll just call them exam 1, exam 2, and exam 3. Like we can say they're calculus, physics, and chemistry. Here we have some numbers. So we have 60 students take exam 1, 39 students take exam 2, 44 students take exam 3, 27 students take exam 1 and 2, 22 take exam 1 and 3, 28 take exam 2 and 3, 19 take all 3 exams, and 13 students take none of the exams. And then how many students are there at the whole school? So this is where the principle of inclusion and exclusion can help us a lot. So if we use our set notation that we looked at above, let's call A the set of students who take exam 1, B the set of students that take exam 2, C the set of students that take exam 3, and then we can translate all of these statements into these kind of shorthand statements here. So basically we see the number of people who took each, the number of people who took both, the number of people who took all 3, and then here we use the C to denote the complement, which is basically how many people took none of them. And so the question is, how many students are there total? And so in order to count how many students there are total, we want to sum the number of students who took at least 1 exam, which is the union of A, B, and C, plus the number of students who took no exam. And then we could simplify this to just the union plus 13. And we need to determine the size of the unions, even though we only have information about the size of the sets themselves and their intersections. So we can draw a Venn diagram again here, looking at, in this case, we have 3 different circles. So we have exam 1, exam 2, exam 3, and we can see if we sum up directly the number in this circle, plus the number in this circle, plus the number in this circle, we're going to end up counting everything in this section once, this section once, this section once. However, we're going to count everything in this section twice, this section twice, and this section twice. And then we're going to actually count this section in the middle 3 times because it's within each of the circles. So if we go back to how we correct for overcounting here, we'll need to actually subtract some stuff out and then add some stuff back. So here, we can try the following. So let's say we take, everything, we add everything in set A, plus everything in set B, plus everything in set C. And then we need to subtract out some intersections like we did before. So here, let's subtract out the intersection of A and B. In that case, we end up counting this section once, this section once, this section once, this section twice, this section twice. And then since we're subtracting out the intersection, before we were counting this twice and counting this 3 times, now we're counting this once and counting this twice. So that's promising. Well, now we're only counting this section once. So let's then subtract out A intersects C. So in that case, if I subtract out this intersection, then I'm going to count this once and count this once. So I'm really close to counting everything once. Let's subtract out B intersects C. Then I'm counting this one once. And then now, since I subtract out it again, now I'm counting this middle side or the middle section 0 times. So this is very close, but now we're missing this again. So in order to count the whole thing, I need to add back in the intersection. So instead of 0, then I get 1 again over here. So it's just, this is a prettier way of writing it than my handwriting. So in order to count every section once and exactly once, we have to do this following identity. So basically we take the number of students in set A plus number of students in set B plus number of students in set C. We subtract out the pairwise intersections as I drew out on the top left. And then finally we have to add back that center one because we subtracted it out 1 too many times. And then this is basically principle, we call this principle of inclusion-exclusion for 3 sets. So this is sort of a generalization of the one that we just did for 2 sets, which we remember was just, I'll write it here for comparison. For 2 sets, it was just A union B equals A plus B minus A intersect B. And so if we go back to the problem that we were doing, which is like how many total students are there, we can just plug in the numbers. So there were 60 that took just exam A, 60 that took exam A, 39 that took exam B, 44 that took exam C, 27 that took A and B, 22 that took A and C, 28 that took B and C, and then 19 that took all of them. So if we compute all this arithmetic, we'll get 85. And then remember, we had to add in how many students didn't take any. So we can add 13, and then we get the total number of 98. So this definitely gets a little bit more complicated, right? If we compare the formula for 2 sets versus the formula for 3 sets. But it also kind of follows a pattern. So we can look at basically this pattern that we're doing. So we add the sizes of each single set as step 1. Then we want to subtract the sizes of all sets that are intersections of 2 of the original sets. Then we want to add back the sizes of all sets that are intersections of 3 of the original sets. And then if we were to keep expanding this, say we had more sets, then we would subtract out the sizes of all sets that are intersections of 4 of the original sets, and so on and so on. So we always add all the intersections of any odd number of the original sets, and we always subtract off all the intersections of any even number of the original sets. And then we continue until we reach the intersection of all of the sets. We won't go into proof for this, but if you're interested, it's something that you can look up online, and then if you have any questions about it, you can post it in Piazza. But for just this course, we'll just focus on applying this principle, and then kind of in your own time, you can look up how to actually prove it. Any questions?
Please, if the set is a disjoint set, you still need to follow the steps for pi.
Sorry, say that again.
If the set is a disjoint set, you still need to follow the rules for pi.
So the question is, if the sets are disjoint sets, do you need to follow the rules for pi? you don't, because if they're disjoint, that means there's no overlap, right? So if you have two sets A and B and there's no overlap, that's sort of equivalent to saying there's a overlap of 0 in here. And so pi still, it applies, but you don't need to apply the formula because you can just directly add A and B. And so we could see that by saying, okay, A union B, again, equals A, size of set A plus size of set B plus, minus the intersection. And so when the set is disjoint, what that means is the intersection is 0. So if it's disjoint, you can apply pi, but basically it'll just give you 0 for that term.
Okay.
Miss Wendy,
Yep. Did you have a question?
you said we add A and C in the ending. Yeah. You said after we, in the ending, we have to add A intersection B intersection C. But it says that that is the number of students who take no exams. But wouldn't that actually be the number of students who take all 3 exams?
Yeah, so you're saying here the total number of students at far side is, right?
Yeah.
Yeah. It's just a typo.
Okay.
So 13 is the number of students that take no exams, and we need to add that to the number of students who take at least 1 exam.
Okay. Thank
Yeah.
you.
All right, so I want to do a couple more practice problems here. Here, just to make sure we get this, understand this together. So here's another example problem where we can use principle of inclusion and exclusion. So let's say there's 67 students on the math team, 58 students on the debate team, and there's 22 students on both teams. So how many students are on at least one of the math and debate teams?
I think you use the first formula that says A plus B minus A intersection B.
Mm-hmm. So how do we apply that to here?
So it will be 67 plus 58 minus 22.
Right, so let me just write this out. So remember we had this principle of inclusion-exclusion, which is the size of the union of 2 sets is equal to the size of one set plus the size of the other minus the intersection. So if we apply that here, the number of students on math or debate equals the number of students on math plus the number of students on debate minus the number of students on both. And this gives us 103. Cool. Pretty straightforward. Let's do another example where there's a bit more sets here. So here we have 36 at a high school. There's 36 freshmen that take Spanish, 45 take French, 19 take Chinese. Of the people who take Spanish, 12 take French, 4 take Chinese. So that means 12 people take French and Spanish, 4 people take Chinese and Spanish. And then there's 8 freshmen that take French and Chinese. And then 2 of them take all 3 languages. So then how many freshmen study at least one foreign language? Who wants to take a stab at this one?
So it will be 36 plus 45 plus 19 minus 12 plus, no, minus into bracket 12 plus 4 plus 8, then close the bracket plus 2.
Right, so this is just principle of inclusion exclusion applied to 3 sets. So if we write out this arithmetic, I think we will get 78. You guys can check. All right. Anyone have any questions on these two? If not, we'll move to a different question. So here's one that's a little bit, it's using the same principle, but it's a little bit less obviously principle inclusion exclusion. So this one says, how many positive integers not exceeding 100 are multiples of 2 or 3, but not 4? So does anyone have any ideas on this?
Yes.
Go ahead.
Yeah.
An idea for this. Since there aren't going to be that many, we can just try to list it.
We could try to list it, but is there a way that we could count it without listing it?
Yeah, you have to do 100 divided by 2, which should give you 50. Then 100 divided by 3, which should give you 33. And you add them. After, you have to divide 100 by the 4, which should give you 25. So you get 83 minus 25. Then put that answer aside. Then you divide the 100 by 6, which will give you 16. So the answer you go for 83 minus 25, you add it to the 16 to get your final answer.
Okay, that's really close. So let me write down what you said. So first, it looks like you're counting multiples of 2. And there's 100 divided by 2, which is 50 multiples of 2, right? So that's just 2, 4, 6, 8, all the way up to 100. Then you're counting multiples of 3, which is 100 divided by 3, and we just floor it, which is kind of rounding down to the nearest integer. And there's 33 of these, and that's 3, 6, 9, all the way up to 99. And then you said we need to subtract out multiples of 4. That's right. Here, there's 100 divided by 4, which is 25. And then you also said we needed to count multiples of 6, which is, if we round that down, we get 16. So let's see how we combine this. So in order to count, let's first ignore this part that says, but not 4. So how many positive integers are multiples of 2 or 3? So that's principle of inclusion and exclusion. So we want to take multiples of 2 plus multiples of 3 minus multiples of 2 and 3. So remember, and in this case, we say A is A is multiples of 2, B is multiples of 3, and then the intersection is multiples of 6. So this gives us 88 minus 16 equals 72. And then we have this part that says, but not 4. So now we also have to subtract out 25. So our final answer is 72 minus 25, which gives us 4, I think I did something wrong. This gives us,
No, 83 minus 16 will give you 67. Not
yeah,
70.
sorry. Yeah, I was like, I think this number is wrong. So this is actually 83 minus 16. This gives us 67. And then here, we want to take 67 minus 25, And this gives us 42. Cool. So everyone see how principle of inclusion-exclusion helped us with this one? And so to the first point about listing them out, it is possible to list them out, but I think you'll get to the point where, like, you know, if I said instead of 100, I said 10,000, you're still going to be able to use the same principle to calculate that, but it's going to be harder to list it out in that case. Let's do a couple more together. So here we'll define something called a relatively prime date as a date for which the number of the month and the number of the day are relatively prime. Did you all learn about relatively prime numbers?
No.
No, please.
Okay. So in number 3, you all learn about divisors, right? So, and did you learn about greatest common divisor?
Yep.
Yeah.
Okay, cool. So 2 numbers are relatively prime if their greatest common divisor is 1. So I guess it talks about here, the greatest common factor of 6 and 17 is 1. So for example, like 2 and 4 are not relatively prime because 2 divides both of them. Or 6 and 8 are not relatively prime because 2 divides both of them. 5 and 20 are not, or 15 and 20 are not relatively prime because 5 divides both of them. So in this case, relatively prime just means none of the, there's no common factor other than 1. And so we'll call something a relatively prime date if the greatest common factor of the number of the month and the number of the day is 1. Here there's an example. So June 17th is a relatively prime date because 6 and 17 don't share any common factors. The GCD is 1. Today, which is June 23rd, is also a relatively prime date because 6 and 23 don't have any common factors. And so here the question is, how many relatively prime dates are in the month with the fewest relatively prime dates? This is a little bit tricky. Anyone have any ideas? So
Well, maybe we could
go ahead.
start by looking at the months that have a prime number, and start by trying to see which days in those months would pair to give us the greatest common factor of 1.
Yeah, so we want to find the month that has the fewest relatively prime dates. So if we look at a month that is a prime number, we could see, well, basically if we look at a month like January, for example, then all of the dates are going to be relatively prime. If we look at a month like February, then only about half the dates will be relatively prime. And so what we see is, or if you think about it, you could also work through it, but if you think about it, like the months that have the fewest relatively prime dates are going to be the months where the month has a lot of prime factors in it. So some good candidates for this might be June, because June is 6, which is 2 times 3, or December maybe, which is 12, which is 2 times 3, 2 squared times 3. And so we might start with June because June has 30 dates and December has 31 dates. And 31 is relatively prime, but we can try, right? So for June, let's try to count how many relatively prime dates are in the month of June. So how might we do this?
Well, we could start by excluding the multiples of 6 in the month of June. That way we know they won't give us relatively prime, because when you add a multiple of 6 to 6, it's going to give you another multiple of 6.
That's true. So let's see if we could break this down systematically. So here, I might actually say, let's use complementary counting for this. So we could take the total number of dates, which is 30 in June, and then we want to subtract out the number of dates that are not relatively prime. To get the total number of relatively prime dates. And then in order to get the total number of dates that are not relatively prime, since June is 6, which is 2 times 3, we basically want to count the total number of multiples of 2 or 3. And so this kind of starts to look like principle of inclusion and exclusion. So for number of multiples of 2 or 3, remember this is number of multiples of 2 plus number of multiples of 3. And then since we're overcounting, we need to subtract out number of multiples of 6. And so this is now very similar to the problem we just did. So out of 1 to 30, there's 30 divided by 2 multiples of 2, which is just 2, 4, 6, 8, all the way to 30. And then number of multiples of 3 is 30 divided by 3. That's 3, 6, 9, 12, all the way up to 30. And then subtract out multiples of 6 because we're counting them twice. There's 5 of those. So this gives us 15 plus 10 minus 5, which gives us 20. So that means the total number of relatively prime dates is 30 minus 20, which is 10. And so that answers part of it, which is like for June, how many relatively prime dates are there? You could do an exercise where you go through all of them, or you can think about like, February only has multiples of 2, so you're going to have more relatively prime dates. March only has multiples of 3, so there's more relatively prime dates. April, again, is 2 squared, so the only things that are not relatively prime are going to be the even ones. The ones that have larger primes, like April, which is 5, or July, which is 7, or November, which is 11, those are going to have way more relatively prime dates as well. And so the only really other option is maybe December, that also has factors of 2 and of 3. But because December has one more date, it's actually going to be 31 minus 20, which is 11. So June actually has the fewest relatively prime dates. And then we just calculated that was 10. So that's the answer. I won't go into all of the other months, but if you're not convinced, maybe go through and see how many relatively prime dates there are in the other months. Any questions on this one? All right, so we have about 15 minutes left. I want to really quickly touch on combinations, and then we'll do a little bit more of that in the next week. So this is pretty different again from principle of inclusion and exclusion, but later on we'll see how to combine all of these concepts together. So for committees, this is one type of counting problem. And so let's look at an example. So Jill and 8 of her friends form a volunteer group to help build schools. Of the 9 volunteers, 4 of them will serve as a committee of organizers. And how many different ways can the committee of 4 organizers be selected from the group of 9 volunteers? And so one term you'll see a lot in counting is combination. We'll talk more about how combinations are different from permutations. But basically in a combination, order doesn't really matter. So for these 4 organizers, it doesn't matter the order in which I picked these 4 organizers. It just matters that I picked 4 organizers as a set. And before we talk exactly about how to solve this one, here are some examples of some other problems that are representing the same type of counting problem. So Tom has 9 shirts to pass out to members of his baseball team. 4 of the shirts are identical orange, 5 of the shirts are identical blue, and how many distinct ways can Tom pass out the 9 shirts? In how many ways can 4 of the 9 members of the Scott family get together to go to Sunday brunch? Or in how many ways can 4 A's and 5 B's be arranged to form a word? All of these are sort of choosing 4 things from 9 things, or choosing 5 things from 9 things. So they're all ultimately counting the same thing. Does anyone have any questions about why these are very equivalent counting problems?
I was just wondering how you would be able to tell that, okay, here they're asking for order, here they're not asking for order, so that you know whether to use a permutation or a combination to solve the question.
Yeah, that's a good question. I have an example later on where we'll talk about it, but generally when people say that things are distinct or they are some sort of order, like how many ways can people sit in a line of chairs, or how many ways can people pick like a president, vice president, secretary, then the order matters, because whoever you pick first, it's different than picking them second. But when the question says the shirts are identical and you can like pass them out, or the committee is picking 4 organizers and the 4 organizers, there's no like positions to them, then you would want to use a combination.
Okay, thank you.
Yeah. So let's kind of look at how to actually compute a combination. And some of you might have already seen this in the Art of Problem Solving book. But let's in particular look at this last formulation, and how many ways can 4 A's and 5 B's be arranged to form a word. And this is tying back to the overcounting stuff that we did at the very beginning of today's lesson. So if we had 4 A's and 5 B's, then the total number of ways to order them, remember, is 9 factorial, and then we want to divide to account for the overcounting. So in this case, because there's 4 A's and 5 B's, we want to take 9 factorial, divide that by 4 factorial, and divide that by 5 factorial. And then if we expand out the factorials, what we see is we can actually kind of cancel out these 5 factorials, and then we actually get 9 times 8 times 7 times 6 divided by 4 factorial. In this case, it's 126. And then we can basically use this analogy to see why the problem of selecting a committee of organizers among Jill and her friends is identical. So for example, we could line up the 9 volunteers, pass out 9 shirts, 1 for each volunteer. And then maybe 4 of the shirts say A on them, 5 of the shirts say B on them. And then the 4 organizers who get shirt A become the volunteers. And so when the volunteers put on the shirts, each combination of shirts forms a combination of 4 A's and 5 B's. So then for each way to form a committee of organizers, there's also one arrangement of the 9 letters. And for each arrangement of the 9 letters, there's a committee of organizers. So there's sort of a one-to-one correspondence there. And so the number of combinations is the same if we're looking at our original problem of Jill and 8 of her friends. So this is also going to be 9 factorial over 4 factorial times 5 factorial. And this is a really common type of problem, as well as like computation that we'll do. So we'll introduce some notation. You can use the similar type of notation as permutations, but instead of using P, we'll use C. Or more commonly, you'll see it written like this, 9, and we call this just like 9, choose 4. That's how you could say this. Oh, I guess sorry, it's written here. So So basically the number of ways to choose 4 people out of 9 to form a committee. And so 9 choose 4 is just 9 factorial over 4 factorial times 5 factorial. And more generally, if we had, say, n choose k, like we have n things where n is greater than or equal to k, if we want to choose k things from n, then we actually can write this as n factorial, k factorial, n minus k factorial. So when n is 9 and k is 4, that's 9 factorial times 4 factorial times 5 factorial. Does anyone have any questions?
Yes, so it was 9 factorial divided by 4 factorial, 5 factorial. So does it mean that you can swap the 4 and the 5 and bring the 5 before the 4?
Yeah, that's a good observation. So in general, you can say in this case, you're saying 9 choose 4 equals 9 choose 5. Yeah, you can swap the 5 and the 4.
Okay, thanks.
Yeah. All right, so let's do one practice problem to start. Yeah. So this is actually what you just said, but with n and k. So can someone just explain what this is saying and why it might be true?
Well, what this is saying is that n choose k is equal to n choose n minus k, due to the fact that in the when you actually put it into a formula form, it's n factorial over k times n minus k factorial. So when you switch it around, you'll end up still having n minus k factorial times n minus k, n minus n minus k factorial times n minus k factorial.
Yeah, so if you write it out, you kind of get the same thing. Another way to think about this that's more sort of a counting argument is the version on the left is how many ways are there to select k things from n things. And then the version on the right is actually counting sort of the complement. How many ways are there to select n minus k things from, or maybe not directly the complement, but n minus k things from n things. So basically you can think of one as like I'm choosing k things. The other one is like I'm choosing the set of things that are not being chosen, if that makes sense. So for example, if we look at the example of A's and B's, let's say we have, we want to arrange k A's and n minus k B's. So this is total, there's total n A's and B's. Then the total number of ways I could arrange this, I could think of it as I'm going to do 9 factorial and then correct for overcounting. Another way you could think about this is like I have n spots and I want to choose k of them. And then once I choose the k of them, I'm going to put a's in those spots. So that's going to be n choose k. Another way you can think about this is I have n spots and I want to choose n minus k of them. And once I pick those spots, I'm going to put the b's in them. And so all of these are sort of counting the same thing. Cool. And then this problem is actually related to another question that someone asked earlier, which is how do we know the difference between combinations and permutations? So take a minute, we'll read these together, and then want someone to explain what the difference is between these two problems. So the first one is Lisa is designing a banner for a school play. The banner consists of 4 vertical stripes, such that each stripe is a little bit thicker than the one before it. She must choose 4 different colors to paint the stripes out of 9 available colors. And how many ways can she do this? And then the second question is, Tim is designing a banner for a school play. The banner consists of 4 horizontal stripes. He asks Heather to grab 4 differently colored cloth stripes from the supply closet. When Heather arrives at the supply closets, she finds that there's 9 different colors of cloth stripes. And how many distinct ways can she choose from among the cloth stripes to help Tim with his banner? So someone want to take a stab at the first question? How many ways can Lisa design her banner?
Well, I think the first question is the permutation question of the 9 of the 4 colors out of the 9 available. So it would be 9 factorial over 4 factorial, which is 9 times 8 times 7 times 6. And that would give us the answer to how many ways in which she can choose the colors for the banner for school play. And then I think and the next one is a combinations question, because I didn't notice any order in it. So it would be the same 9 choose 4, but our answer would be 5 over 5 factorial times 4 factorial, which is 126.
Yeah, so one small thing I'll say is when you said the permutation, that's correct, except it's not 9 factorial over 5 factorial or 4 factorial, it's 9 factorial over 5 factorial, because we want to do 9 times 8 times 7 times 6. In the second case, you're right, it's combination. So basically it's 9 times 7 times 7 times 9 times 8 times 7 times 6 divided by 4 factorial to give us the answer. Does everyone see why these two are different? Does anyone have questions about why one is a permutation, why one is a combination?
No, why is the first one permutation?
So when we're reading the question, it says the banner consists of 4 vertical stripes. Each stripe is a little bit thicker than the one before it, so maybe it looks something like this. There's a banner. And then we have, no, that's a bad drawing. Each one is a little bit thicker. Let's go with that. All right. And then she needs to pick 4 different colors. So here the order matters. Whatever we paint, this one is different than this, than this, than this. And so if there's 9 different colors and they have to be different, then there's 9 possibilities for the first one, 8 for the second, 7 for the third, and 6 for the fourth. So the order matters in this case. In the second case, the order doesn't matter because Heather is just picking 4 cloth stripes, and it doesn't matter which order she takes them in because she just like takes a bundle and brings them to Tim. Does that help?
Okay, thanks.
Yeah.
Miss Wendy, I was wondering if there was ever a situation where you'd have to use both combinations and permutations to count out an answer in a question.
Yeah, it's definitely possible. Let me see if I can find one. We can try this one. It's not quite the same though. This one's, let's do this one. It's not exactly right what you're saying, but there are ways in which questions might require both. So let's do this one. I know we're a little bit over. We'll do this one quickly and then we'll wrap up. So this question is, a license plate consists of 2 letters followed by 2 digits. For example, MP78. Neither the digits nor the letters may be repeated, and then neither the letter O nor the digit 0 may be used. And then when I read from left to right, the letters must be in alphabetical order and the digits must be in increasing order. How many different license plate combinations are possible? Any ideas?
Well, first we can start off with the fact that they've reduced the number of letters in the alphabet and the number of counting numbers, the number of numbers we can use. So 26 letters in the alphabet, but we can't use O. So there's 25 available letters for the first place in the license plate. Then there's one available for the next place because it has to read in alphabetical order. And then for the numbers, usually we'd have 10 available, but we can't use 0. So now there are 9 available. And since they have to be in an increasing order when read from left to right, you'd start with 9 available options and you'd have only 1 left.
So you have the right idea, except for why is there only 1 left once you have
because of the fact that it said that you'd have to read in alphabetical order and increasing order, so you can only have 1 option left if you want to follow with that restriction.
I see. Well, it doesn't have to be in consecutive. So in this example, we have 7, 8, but it could also be MP 7, 9. So for example, if there's 7, the next one could be 8 or it could be 9.
So it's So it's rather 25 times 24 and then 9 times 8.
So that's close. If you do 25 times 24, you're not going to get the alphabetical order because then you're counting both MP and PM. So the way I would do this is viewing this as a combination. So if I choose 2 letters out of 25, I'm going to get 2 distinct letters. And then for every pair of 2 distinct letters, there's 1 way to put it in alphabetical order, right? So say I choose B and X, then I have to put it in the order BX. Similarly, for digits, I could choose 2 digits. Maybe I pick 2 and 5. Then I have to put it in the order 2, 5. So there's actually 25 choose 2 ways to pick the 2 letters. And then there's 9 choose 2 ways to pick the 2 digits. And then the way we combine this isn't exactly permutation. This is just multiplication rule that we learned, but we would multiply them together to get the total number of license plates. And if we multiply this together, I think we will get this number. You guys can double check my math. There's a little bit of lag, 10,800. Anyone have any questions on this?
So instead of trying to multiply by 24, we could, or instead of doing the choosing in combinations, could we also, like, when we find out what our first letter is going to be, subtract that number, that letter, and then the other letters that come before it from the total amount of letters we are able to use, and then multiply?
Well, the thing is, you don't know what that letter is going to be. So unless you're going to do casework to do it, it's going to be really hard. The other thing you can think about is, like, how does this question generalize? Like, instead of it saying a license plate consists of 2 letters followed by 2 digits, what if the question was the license plate consists of 3 letters followed by 3 digits? And so in that case, the way you could solve that, it would be really hard to do that with casework, because then you have to figure out, like, for the first letter, what happens, for the second letter, what happens, for the third letter, how many options are there? But if you had 3 letters, you could just do 25, choose 3, and you know that when you have 3 letters, there's only 1 way to sort of sort them in alphabetical order. So I think what you're
Okay.
saying, it like makes sense logically, but when you actually do the work, you're gonna actually have to count a lot of different cases.
Okay, thank you.
Yeah, no problem. All right, we're a little bit over time here. I would really encourage you for homework to go through the handout that I sent out. I would go through all of them through committee forming exercises, and in the handout there's also solutions. And then there's a couple extra pages here. If you have time, go through it. Otherwise, we will cover it next week. And then for each of these sections that we did, overcounting, principle of inclusion, exclusion, and committee forming, there's exercises, and the exercises also have solutions. If you have any questions on any of the material or on any of the exercises and the solutions, feel free to post in our forum, and then we can help each other out. Thanks everyone for coming, and I think we will be posting this video as well later on, so you can refer back to it. I will see you all in office hours on Friday.
Okay, thank you, Ms. Wendy.
All right, thank you everyone.